Good morning everyone. First and foremost, I would like to thank Department of Physics and CP Sir, Namchi Government College and Sikkim University to provide one such a platform to make a video for partial fulfillment of BSc Honours on Physics at 5th semester June to December 2020. My name is Pranita Pradhan and my roll number is 18NS0008, and this topic carries 25 marks instead of our practical examination or sessional B. In this video, we will be discussing about classical Langevin theory in diamagnetism.
So moving on, all kind of materials, whether metal or insulator or semiconductor, exhibits magnetism according to their magnetic properties. So they can be classified as diamagnetic materials, paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. So when subjected to a magnetic field, all materials developed a magnetization which is either parallel or antiparallel to the applied magnetic field. So in diamagnetism, this magnetism is antiparallel to the applied magnetic field, which means that this type of materials are repelled in the region of strong magnetic field. So as compared to paramagnetism, they are attracted to the region of strong magnetic field, which is why it is parallel to its applied magnetic field. So moving on, let us first define some terms. Magnetization. Magnetization, it is defined as the magnetic moment per unit volume. What basically is magnetic moment? Magnetic moment is also known as magnetic dipole. Symbol is mu, and we know that it is a vector quantity. So basically, when two opposite poles forming a system are separated by a small distance, which is well known as magnetic dipole moment. If this dipole is placed in an external magnetic field, it experiences torque and rotates itself in a particular direction. So if torque experienced by this magnetic field, the dipole in magnetic field, then the magnetic moment, dipole magnetic moment is defined as mu cross B equals to tau. So if tau experienced by the dipole in magnetic field is then the magnetic dipole moment is defined as mu cross B equals to tau. So moving on to the next term, magnetic susceptibility. And what is magnetic susceptibility? It is basically a measure of the ease with which a unit volume of a materials can be magnetized by a magnetizing field. So if I denote magnetizing susceptibility as H, magnetizing field as H, so magnetism, so this magnetism will be M. So then we can write magnetic susceptibility equals to M over H. This is dimensionless quantity because the dimension of magnetizing field and magnetism are same. So therefore they becomes dimensionless quantity. Magnetic susceptibility is very important characteristics which defines the magnetic property of the atom and relates to the microscopic properties of the solids. It is negative for the diamagnetism substances and positive for the para, ferro, and ferrimagnetic substances. So now we come to the diamagnetism. Diamagnetism is the occurrence of negative susceptibility which arises from Lenz's law. Lenz's law we already have studied. So what Lenz's law says that when the magnetic flux through an electric current is changed, an induced current is set up which has the direction such as to oppose the change in the magnetic flux. In diamagnetism, we considered Bohr model of atom in which central nucleus which is surrounded by electron revolving around it with some frequency, say omega naught. So when we apply an external magnetic field, the flux changes. So what happens according to the Lenz's law, the current changes. So as to oppose the change in flux, this appears as a change in the frequency of revolution of electrons. So according to the Bohr's model of atom, we have an electron revolving around the nucleus. So according to the Lenz's law, the change when the materials is kept inside magnetic field, this appears as a change in the frequency of revolution of electrons. So now let's understand it mathematically. Let us consider force on an electron in a circular orbit. Here we are considering Bohr's model of atom. So there is a circular orbit. So in the circular orbit, in the absence of magnetic field, what we have? The force we have are firstly, the orbit is circular. So we have centripetal force. For centripetal force, it is given by F equals to mv square divided by r, where v equals to omega cross r. So when we replaced v in the above equation, we get F equals to m omega square r. So from here we get centripetal force, and again we have another force which is electrostatic interaction between the nucleus and the electron. So that electrostatic energy is given as jet E square divided by 4 pi epsilon naught r square. So here where is what is E? E is the charge of electron, jet E is the charge of nucleus, m is the mass of electron, and r is the radius of circular orbit. So from these two equation, from the above two equation, that is m omega naught square r, which equals to jet E square divided by 4 pi epsilon naught r square. From these two equation, we can calculate the value of omega naught. So the frequency with which the electron is revolving is omega naught equals to root over jet E square divided by 4 pi epsilon naught m r cube. It is the frequency with which electron is revolving around the nucleus in the absence of magnetic field. So now when we apply some magnetic field, in the presence of magnetic field there is Lorentz force. Lorentz force on electron moving with velocity v is given by v cross b. Here negative sign is due to the negative charges. So the final equation will be F equals to minus E into omega cross r into b. So now assuming that the applied magnetic is perpendicular to the orbit, if this is perpendicular to the orbit, theta becomes 90 degree and sin theta becomes 1. So we can write it as F equals to E omega RB with negative sign. So where the omega is the frequency of electron in the presence of magnetic field, therefore the final equation of the force can be written as the total force, which is m omega square r, equals to the electrostatic interaction ZE square divided by 4 pi epsilon naught r square, which is equals to the Lorentz force E r omega b. So just taking this to the left hand side, we get this equation equals to 0. So now divide the whole equation by m into r. It becomes like this: omega square plus E r omega e divided by m r minus ZE square divided by this. Now looking at the previous equation, this is the value of omega naught square. This whole term is basically the value of omega naught square. So putting omega naught square in place of this, it becomes omega square plus EB divided by m into omega minus omega naught square equals to 0. So here it becomes quadratic equation. So when we have to solve this quadratic equation, the solution becomes omega equals to minus EB by m, which is the value of b, plus minus b, which is EB divided by m whole square, plus 4AC, which is 4 omega naught square. Here the value of A is 1, so A 4AC will become 4 omega naught square whole divided by 2. So by solving this, we get plus minus root over omega naught square plus EB divided by 2m whole square minus EB by 2m. If EB by 2m is much less than omega naught, so we can write omega equals to plus minus omega naught minus EB by 2m. So now what this shows is that the applied magnetic field changes the angular frequency from omega naught to omega. So now when we change the frequency from omega naught to omega, it is the application of magnetic field. So there is the sign plus minus in the equation, which means that the electrons having orbital moment parallel to the field are slowed down, and those moments are anti-parallel are speeded up by the amount EB by 2m. So looking back to the equation again, this is the angular frequency of electron before the application of magnetic field. So when we applied magnetic field, the frequency becomes omega. From omega naught it changes to omega, and the factor by which it changes is EB by 2m. So this EB by 2m is called the Lamarck frequency, and the theorem by which we derived it is known as the Lamarck theorem. So now the change in the frequency will give rise to a change in the orbital magnetic dipole moment, that is, a magnetic polarization or magnetization take place. So this is how magnetization phenomena take place. The change in the frequency gives rise to change in the orbital magnetic dipole moment. This is basically change in the magnetic polarization, and in turn magnetization take place. This is because the change in frequency is equivalent to an additional current. So as Lenz's law says, the additional current is induced, so those frequency change is equivalent to the additional current. So now we will calculate how much is this additional current. So the current for each electrons due to the change EB by 2m, which is the Lamarck frequency, is given by charge into revolution per unit time, which is nothing basically but frequency. So I becomes Q into F. Q equals to ZE, which is charge. F equals to omega divided by 2 pi, frequency, and Lamarck frequency, which is omega equals to EB divided by 2m. So the current becomes minus ZE divided by 2 pi into EV divided by 2m, which equals to minus ZE square B divided by 4 pi m. So magnetic moment of this current loop equals to I into area of loop. So if rho is the radius of the loop, then area equals to pi into rho square. So here we have calculated current as minus ZE square B divided by 4 pi m into area of loop pi into rho square. So magnetic moment becomes mu equals to minus ZE square B rho square divided by 4 m. So there is again the negative sign, which signifies that the induced magnetic moment is always opposite to the applied field. If this field is in z direction, then this rho can be written as rho square equals to x square plus y square. But we have to use averages. Why? Because all the electrons in an atom do not have the same radii. So we cannot use the distance upon electron from the field axis. We have to work with averages. So what we take is the mean square distance of electrons from the nucleus is considered as average of R square equals to x square plus y square plus z square. Here in all the three directions they are similar, so we can write x square equals to y square equals to z square. So R square can be written as 3 into x cube. Similarly for the rho, we can write rho square equals to 2x square, since rho square equals to x square plus y square. So if you want to derive an equation between these two, we can divide it, and it looks like R square divided by rho square equals to 3 by 2, and it can be written as like this also. So in views of this magnetic moment, which was minus ZE square B divided by 4m into rho square, now becomes minus ZE square divided by 4m into B into R square. So this is basically magnetic moment. So now when this magnetic moment is multiplied by n, here n is the number of atoms, so magnetism becomes n into mu, and magnetic susceptibility is m over h. So we can write here h can be written as B divided by mu naught, since B equals to mu naught h. So the susceptibility becomes mu and mu naught divided by B. So putting the value of mu in the equation, we get susceptibility, magnetic susceptibility equals to n mu naught divided by B into mu. So this is the susceptibility of the diamagnetic materials, and this is called classical Langevin result. And the theory we were doing is Langevin theory of diamagnetism. So now look at this equation. This shows that the susceptibility is independent of temperature. I mean, there is no term which denotes or depends on the temperature, which means that the susceptibility is independent of temperature. This can be attributed to the fact that electronic structure are always independent of temperature, and so as the diamagnetic susceptibility. So yeah, this was all about the Langevins result and diamagnetics classical materials.